Hello everyone, my name is Simon Walker. I'm a researcher at the University of Warwick, which is just down the road from here. I've not come far today. And I'm going to be talking about studying astronomy with Python especially at the University of Warwick. So we're quite a big group now. We've expanded quite a lot over the last few years. We've almost doubled in size. And a very large fraction of us use Python for basically everything. One of the points I'm trying to get across with this talk is how little we need to reach for external tools, for data analysis, for visualization, all of this kind of stuff. So the majority of us use Python, which I think is really great. So why did we pick Python? I mean, Python is a fantastic language and it has fantastic libraries for not just astronomy, but sciences in general. Typically, the analysis process follows very similar principles, and Python just kind of fills all the gaps and really helps us with our workflow. So the general process that I've come up with, so you start out, you have this fantastic idea for some new research you want to do. It's really exciting. You convince all of your funding groups that you have the go-ahead. That's quite a tricky proposition to start with, but let's not go into that. And then you get some time on some big fancy telescope to do whatever you want to do, and then you get some data back. So that's the first box there, data collection. Typically that doesn't involve Python, but Python can be used. A lot of the pipelines are written in C and C++ because these telescopes are predated Python as a sort of useful tool. So then the second box I've got here I've called manipulation. This is kind of badly named. What I really mean is anything with your data that you know is wrong, systematic effects that you need to correct for. Things like issues with the optical path, you get vignetting on the images and things like this. So that's removal of known systematic effects. That's very important to do. Then we get to the fun part, the analysis. This is where you apply what you think is happening and you test it with what you've observed. This is typically where a lot of time is spent, because that's where the new ideas are, that's where they're applied. And then the final step is visualization. So you want to present your results to someone else. A very easy way in science to do that is to make a graph of something. You can quite easily convey quite complex ideas using graphs. So this is quite a simplified model of really what goes on. This has never happened to me. It's more like something like this. Every line connects to every other line. You tend to go in loops of you have an idea, you try it in the analysis section, you realize it didn't work, you have another idea, and kind of crucially it's not really showing up there, but all of the boxes point to visualization. Visualization is hugely important in science. You have to be able to understand if what you've done is working or not, and the easiest way again to do that is to visualize it. So the exciting part about this is that almost all of those boxes can involve Python. The last three generally do, and especially at Warwick, we use Python for the last three boxes very heavily, with packages like numpy, scipy, and matplotlib especially, which I'll go into more detail in a minute. So yes, Python does all of this. So I'm going to now take the four boxes here and I'm going to break them down a little bit and give some examples of how we do it at Warwick. So we'll start off with the data collection. So I've made the four categories here. The images in the background, I've tried to come up with examples of some of the things we study at Warwick to give you a sense of what we actually do. So in the background here, we have a white dwarf, which is the white star here. It's a really tiny star. It's an old dying star. It's what the sun's going to become. It's the size of the Earth and it has the mass of the sun. It's just really dense. In this artist's impression, we've got it with a companion star, a very nearby star, and you can see it's accreting mass from this star. It's literally stripping the surface of this star and stealing the material. They're really, really cool things. So this is an example of an instrument that members of the University of Warwick. In fact, our head of group is heavily involved in this. Is UltraCam. It's a series of 3 cameras that observe simultaneously and with ludicrously high speeds, like 40 hertz, I think, is the maximum speed. So 40 times a second, this thing can take images. It's a really cool instrument. The software, the analysis software, was written by our head of group, Tom Marsh, and it's written in C++. But he's also written a Python wrapper for the data format that comes out of this pipeline, so that it can be easily accessed and manipulated through Python. Again, this is in C++, but there are wrappers in Python, and there are other tools written in Python to extract the data. This is it mounted on probably the WHT from La Palma. So if we now move on to manipulation, so this again is removing systematic effects, things that you know are wrong with your data that you can't help, but you can get rid of. So in the background here, this is I have to have a little caveat here. This is my research area, so it might be somewhat biased towards this. This is an exoplanetary system. It's an artist's impression again. And what it shows is this is a sun, which isn't our sun. It's one of the other stars in the galaxy, and it's got 4 planets orbiting around it. And this, over the last decade or so, has become much more common than we could have ever imagined. We now think that 80% of all stars in the galaxy, so if you look up in the night sky, 80%, that's 4 out of 5 of those stars, have at least a planet around them, which is just mind-blowing. So manipulation is the removal of systematic effects. Stop doing that. Right. So this is a project I'm involved in. This is the Next Generation Transit Survey. This is a new instrument that we're building, and it's looking for these extrasolar planets around other stars. The key word for this is transit. So the way we look for planets around these other stars is that we observe all of the light from these stars, and we build up time series of the light. And then when a planet crosses in front of the star, the light gets slightly dimmer. I mean slightly. This happened recently in our solar system with Venus transiting the Sun. It's happened a couple of times recently. And if you ever see pictures of Venus transiting the Sun, it's this tiny little black dot on a giant star. That's exactly the kind of thing we're looking for. So it's currently under construction on a mountain in Chile. Stop doing that. This is where it is. It's in the Paranal Mountain in Chile, northern Chile. Yep. And I've got some pretty pictures of it. So it is currently under construction, which is very exciting for me because I've been working on this project since 2009, and it's being constructed. It's a really exciting time for us. On the top there, you can see the mountain itself. NGTS is the little white building on the left there. On the other hill over there, you can see 2 instruments. The one on the very far right here is an instrument called Vista, and then the one on the very top of the hill up there, that's the VLT. In astronomy, we famously can't name things, so that's the Very Large Telescope, which is also terribly named because it's actually 4 very large telescopes. They can all work together to make a really, really, really large telescope, which, in fact, so 20 kilometers down the road from this site here is another mountain. We're talking, mountain to mountain hops here. That's going to be the site for the next new instrument. It's going to be the biggest instrument, biggest telescope ever built, and it's called the Extremely Large Telescope. On the bottom there, NGTS is minuscule in comparison, I have to say. On the bottom there we have, this is the enclosure. It's a kind of a shed with a roof that slides off. And that's the construction team, or some of them, after construction of the building itself. They look very happy. Directly above it, again, you can see Vista. And over on the hill on the left there, that's the VLT again, the Very Large Telescope. And this is a couple of photos of some of the instruments themselves. Inside that building, there are 12 individual telescopes, each completely robotically automated and controlled, and can look at any patch of the sky, provided it's overhead. And on the right there, one of our engineering team took a nice photo of one of our units with the Milky Way in the background. And it's quite a sight to see the Milky Way and stars in general from a site like this. It's just unbelievable. So the NGTS instrument itself has a few data products. So we have 12 telescopes. If we manage to get a good night, we can get about 20 gigabytes per telescope, which, once you get down to the bottom there, is 86 terabytes per year. This is not even slightly big in comparison to, say, for example, the stuff that Google does every day, or let's say CERN. But it's large for us. We're not entirely sure how we're going to cope with this much data. But on a nightly basis, we have to deal with that 20 gigs per telescope. And we have a computing cluster that can do this. The analysis pipeline that we've got for this is mostly written in Python, which is really cool. We make heavy use of numpy and parallelizations for speed. So I'm going to go into a few examples of how we use those tools. I apologize if this is somewhat basic. So we'll start with numpy. As astronomers, all we ever do is we take images. These are two-dimensional arrays. This is exactly perfect for numpy and manipulation that numpy can do. It's fast, it's vectorized, it's written in C. Quite often we want to do the same thing to each pixel. So if we take an example, I hope you can read this, I'll try and make it a bit bigger. I can make it jiggle. Okay, I apologize if you can't read this at the back, but so this is an example piece of work that we might want to do on an image. So we have our image, and that's the image data term in the function arguments there. And then we have our known systematic effects that we want to correct for. These are in the other three arguments in this function. So we could, in basic Python, just for each pixel, iterate over all the pixels and perform some manipulation on it, pop it out to a list, and then return the list. But if we do it with numpy, it's just one line and a docstring, but one line. And it's less boilerplate. It's much more efficient, and it's much easier to read as well. You get the nub of what this function is doing from that one line, rather than all of the rest on the top line, on the top there. So the other thing we make heavy use of is parallelism. Each one of our computing nodes has 12 cores hyper-threaded, and we have one computer per telescope. So nominally we can do one telescope on one computer with 24 cores simultaneously. We have it a bit easy in astronomy. The kind of analysis that we do on these images, each image is independent of all the others, so it's incredibly parallelizable, which is fantastic. So let's say we have a worker function. It's a kind of simplified worker function. Imagine it's doing similar work to the previous function examples that I've given. So instead of iterating over the list of images that we have, what we do is we create a pool with multiprocessing. We have the same worker function. We construct a pool there, and then we map our worker function over a list of images. And that splits up the list of images into a series of sub-lists, which each then go to a process, and that handles it parallelly. The issue is, what happens if, so pool.map requires a function that only takes one argument. But what happens if we need more than one argument? So I'm going to show one way. This is the way I do it. I'm a big fan of functional programming, and I like partial functions. So this is a more realistic worker function that we have. It takes your image, and it takes 3 measurements of the systematic issues that we want to remove. And then it does some work on the image again. So the way we handle that is we build a partially applied function. So it takes the function of 4 arguments, and it kind of freezes or bakes in the 3 arguments that don't change. In this case, the last 3 arguments. And it returns a new function which only takes 1 argument, which fits our purposes perfectly. We can use it with pool.map, and we can parallelize all of our work in a very simple way. This is not the only way to do it, and I must stress it's really easy in 2.7 above. Below that, less so. You get interesting issues, but there are ways around that. So now we're going to move on to the analysis step. Again, this is the exciting part where you get to test your theory. In the background here, we have a fisheye lens view of the Milky Way. And around the edge, because it's fisheye, I'm sorry, you can't really see that. It's the Atacama Large Millimeter Array, which is an array of dozens, if not hundreds, of radio dishes that all work together to make this giant radio telescope. And that's called ALMA, and it's either under construction or it's operating now. I think a bit of it is operating now. So, in astronomy, we are very lucky and we have modules such as AstroPy, which makes our job very easy. It contains fantastic records of constants and units. Units is really good because floats are dimensionless. You don't know what the float represents. But if you can tag, say, kilograms to it, then you know it's a mass. And it comes in really handy. And it contains units that can be composed as well. So if you have a distance and a time, you can compose that to a velocity. It handles a lot of astronomy data formats. So astronomy is quite an old. It's an old science, and it's been around before computers, and it was around during the early computing times, and that's when a lot of our astronomy standards got fixed. So we have some very archaic data formats, which AstroPy handles perfectly. It handles coordinate and time conversion. This is a pain. So on Earth we have time zones and things like that, which is complicated, yes, and nobody wants to do it. But in astronomy we have to know where the sun is to work out what the time is. We have to know where the Earth and the sun are compared to the center of the galaxy to know what the time is. It has statistics modules, and it has more specialist tools for applications in, say, cosmology, and querying external astronomy databases as well. It's a really great module. It's packed full of stuff. Another library that's fantastic in science in general, but also astronomy, is the uncertainties module. So here each measurement you make will have an uncertainty. It'll have an uncertainty on it. You'll be a certain level of confident about it, and you can encode this with the uncertainties module. So here I've got two examples. U float is an uncertain float. It's saying that the first for A is 2 with an error of 1. So a 50% error. It's not a very good measurement. B is worse. B is 3 with an uncertainty of 2. And then C is the sum of these. When you print out C, you get the answer, which is what you expect, plus an error, which has been handled properly. All the error terms have been added in quadrature correctly. And you can get, if you have the end product result C, you can work out how the error was computed at, I think, all the steps in the computation chain. So that's really nice. For our analysis, we have to come up with what we think is true, our model, and we apply it to our data to see how good we were, to see how good our hypothesis was. So typically you will come up with a model and it'll have certain unknown parameters. You want to find out what these parameters are, but more importantly, you want to know how confident you can be about these parameters. You can measure any number can come out, but if you're not very certain about it, you don't trust your result. So this is a library called MC, which performs Markov chain Monte Carlo, which is a little bit complicated. On the top right here, we have essentially our data. So we have a series of y's measured at a series of x points, and crucially we have error bars on them. So we only trust y to within a certain range. The model here this example here comes straight from the MC website and documentation. It's actually a model where the error bars are too small. So you can imagine, like, for the point in the very top left there, that's way away from all the others, yet its error bar is tiny. So that would suggest that we really trust the measurement and it is significantly far away. It's a bit of a contrived model, but... And on the bottom left here, we have distributions of what each of the parameters are. So the model that is fitted is a straight line. It's y equals mx plus c. So the parameters that have gone into this model are m and c. and also a certain factor as to how much your error bars have been underestimated. This makes it a bit of a more complicated model to explain, unfortunately. On the bottom left there, each of the three distributions, those show our representation of what the value is. MC uses Bayesian statistics, and in Bayesian analysis, your parameters don't have a number, they have a distribution. They have a probability distribution. And then the kind of blobs on the bottom left, they represent how well each parameter is correlated with each of the other ones. Does this parameter depend on this parameter? And this is a synthetic data set. When they came up with this, they knew the values that went into this, and those are the blue lines. And you can see the blue lines they fall within the histogram. They fall within quite a central part of the histogram as well. So this, the last stage, and I've stressed the most important stage, is visualization. You need to look at things when you're studying science in general, but also astronomy. This image is the Hubble Deep Field, which you may have heard of. These are the most distant galaxies. Each blob is a galaxy. That puts it into perspective, I feel. These are the most distant galaxies we've ever observed by using the Hubble Space Telescope to just stare at a patch of sky for ages. Some members of our group study objects which are even further away than this. I feel a bit like Brian Cox here. Even further away than this. They study objects called gamma ray bursts. These are catastrophically big explosions in the very, very distant universe. And we can still see them, and they still outshine everything else in the sky if we observe them, but in gamma rays. So you can't see them, which is probably lucky. You'd be blinded. No, that one. Right. So I've mentioned matplotlib before. This is a really go-to plotting library for Python. These are a couple of examples that I've personally created from my work. They don't really matter what they are, but the top one I feel is a very nice, simple filled contour map, and you get a sense of where the values are and this kind of stuff, the density of where your results are. The bottom plot is probably my favourite plot I've ever done. It's the one I'm most proud of. It's publication. The point I'm trying to get across is that matplotlib creates publication-ready, really professional-looking plots, and that's fantastic. So at no point during your analysis do you ever have to go to an external plotting tool or external libraries in general. This is really fantastic, and it saves us a lot of time. So now, in our work, again, we often have descriptions of how we've done things, why we want to do things, the actual implementation, and the results at the end. And IPython Notebook, I've put IPython, but I mean IPython Notebook is fantastic for this because it encapsulates everything. And I hope this works. It didn't. So here I have an example IPython notebook that I've used for my own personal work. We've got a bit of description at the top, a title, some code that runs. That's fantastic. I can run this IPython notebook. More really boring code. Some histograms, again, matplotlib, embedded matplotlib plots, fantastic for this. More description, really boring description, really boring code, and more plots. So you could actually document your whole process from conception of idea to visualizing it at the end and your conclusions, all from Python, which is fantastic. What else is in here? Nothing. Yep. So I hope that I've conveyed how fantastic Python is and how it's a really great use case for sciences in general, but also in particular astronomy, with the advent of astronomy-specific libraries. And that's not going to work anymore. So thank you for listening, and if anyone has any questions, please feel free to ask. Yes?
The uncertainties of floats module you showed, what's the performance penalty?
It can be quite high. So I've tried, for example, Uncertainties also taps into numpy as well. You can build a numpy array of uncertain values, which is quite cool in itself. And then you can do numpy type manipulation on those. There is a fairly I feel there is a significant overhead. I've tried this with our images, which are 2000 by 2000, which is a large image, and it was quite slow. But I think it also depends on what kind of manipulation you do. If you do a complex manipulation, it'll take longer. Off the top of my head, I don't remember what I was doing with it. Any other questions?
Have you ever come across Open Vision Library, CV, Computer Vision Library for imaging processing?
Testing. Thank you. I have. I've experimented on it in my personal use. I haven't experimented with it for astronomy, for example. I know it's incredibly powerful for what it does. To be honest, no, I haven't tried. It would be interesting. Again, we deal with images. That's all we can do. It's somewhat a strange concept that all we can do is look at things, and that's how we do our science. We wait for photons to reach us. It's very passive. Anything with imaging applications could have a very good use. I know we do convolution of some of our images, or we don't personally, but it is a process that's quite often applied, and this kind of stuff. I've not personally tried, but it's an interesting prospect, yeah.
Just real quick, if Carl Crowder is here, can you come up and we'll set up your...
What do you do with all of the data once you've used it? Because I imagine it can generate so many terabytes a year. And where does it go? When do you reference it later? Store it?
So with the data that we collect, the 20 gigabytes per night, for example, that is the raw data. We have to keep that. We do not want to get rid of our raw data. So we have to store it. We have intermediate products. When I talk about systematic trend removal and things like that, that generates intermediate products as well, which are bigger per image anyway, and there's an equal size of them. So there's about twice as much data than the raw data that we keep temporarily. It's a big issue for us, actually, because our project is relatively small, and we've tried to keep to a really small budget. The budget has been we've spent about £2 or £3 million, which for a project like this is tiny. If you look at something like, you may have heard of the Kepler Space Telescope, which is doing the same technique but from space, that will be 1, if not 2 orders of magnitude more expensive. We're trying to keep it small. Storing our data is currently a big worry for us, actually. Yeah. Thank you.
I know that the main telescope's still under construction, but what's the most interesting thing that you've found using the analytical techniques you've just showed us?
The transiting technique itself? Or do you mean us specifically? Or
you specifically, with the types of techniques from the lecture? At the moment, like you say, we're under construction. We're mostly taking test data. We have some very pretty pictures. We've got some fantastic pictures of the moon, if you'd like to look at the moon. We have some fantastic pictures of different galaxies that have been taken as well. They don't really fit what we're going to do with the telescope in the end, but one of our goals for the commissioning phase is actually to come up with some really nice, clear images for the first press release that we're going to release. In terms of other objects we have observed transiting planets, and we've re-detected them, which is very exciting. That's proving that the instrument can at least do what we try and do with it to a certain level. The objective now is to push that level really low. And we've observed pulsating stars. We've observed, I think we've observed a pulsating white dwarf, this kind of stuff. Okay. Thank you, everyone.